Hi there, this is Robin, and this is the second part of the fourth lecture for STAT 776, which will be on open populations and the Popan likelihood. So before I get into the slides for the second part, there's some corrections for the first part. So there were a couple of typos in the slides. So I had a typo here with n minus x factorial instead of the factorial of the whole thing. So it was correct in the first part up here. So hopefully that wasn't too confusing for anybody. And I don't think I explained very well. Well, first there was some typos in this expression here, so I fixed that up. So hopefully that's more clear now. And I don't think I explained very well why I was changing from this Schnabel census likelihood to this data likelihood, or as we call it, the binomial detectability likelihood. So the reason was just that the Schnabel census likelihood was the version given in lecture 2, but this form is the version that Rachel uses in her notes, both for the closed population likelihood and for the Popan likelihood, which we'll be seeing today. So also the fact that those likelihoods are actually equivalent actually shows that the Schnabel census counts are a sufficient statistic for the capture history data. So that's an interesting case there. And I've got my email here again. Any questions or feedback, I'm happy to receive emails. So today we're going to be getting into the open population data and the Popan likelihood. So the example data set I want to show you is for this beautiful animal, the Maui dolphin, or popoto, which is native to New Zealand. It's found off the west coast of North Island, and it's one of the rarest dolphin subspecies in the world. And we actually have amazing open population capture-recapture data for this subspecies from Hamner et al. 2012. So let's have a look at that data. So I've just got it in our Markdown document here, and I'll also upload the PDF for this. So the first thing to say is that this data represents a huge amount of work. I guess any capture-recapture data represents a lot of work, and for open populations, it's usually going to be over quite some time. This data is over the course of a whole decade, and that means talented people going out on boats and actually observing dolphins, and in this case, actually collecting and analyzing DNA samples. So it's good to remind yourself how much work and talent goes into a data set like this. Here's the citation for this, the paper in which this data is published. And I'll actually just show you this. This is a link to the paper. Yeah, so this is what it looks like. So it's actually a Department of Conservation publication there. Okay, so let's read in the data and have a look at the first few rows. Okay, so the first thing to notice is that the columns have names now, and the names are the years of the surveys. So you can see that there are 7 surveys, and they're not equally spaced. There's one every year for the first 4 years, and then 1 year is skipped, and then 3 years are skipped. So when you're talking about open populations, you can have much longer intervals because you're not assuming that the population is constant over the course of the study. So you need to be aware of what the intervals are. Why do all the first rows have a 1 in the first survey? Just because the animals have been entered in the data in the order in which they were observed, right? So in the first survey, they can only enter the animals that were observed in the first survey, and so on. If you look at rows 2 to 4 here, they were only observed in the first survey and never observed again. And so if we're assuming that the Maui dolphins don't migrate, and that is believed to be the case, did these animals live to the end of the survey and were just never captured? Or did some of them die? And if so, how many and when? We don't know, right? Because it's an open population. So it's a lot more complicated than a closed population. In row 5, this dolphin was observed in the first survey and then in the last survey, but never in between. So maybe we would think that the capture probabilities in between might be smaller. Let's have a look at the last few rows. And here, of course, these are the last dolphins that were observed. So they were only observed in the last survey. And you can see that there's a total of 75 rows in the data. So 75 animals observed altogether. So it's a pretty small data set, but it's not surprising given what we'll see about how small the population is. Okay, let's have a look at the numbers observed in each survey. And I'm actually going to plot them. So I'll make that smaller. So you can see that the numbers are changing a fair bit. But this is different from the closed population, right? So we don't know if these numbers are going up and down because the capture probabilities are different or because the population size is actually changing. So you could sort of imagine maybe the population sort of dipped in the middle and is increasing towards the end. It's pretty hard to tell. So that's the kind of complexity that we're dealing with in open populations. That's what Popan models are trying to decipher. So it's quite a lot more complicated, and it includes information not just about the population size at one time, but the population over time, and also about birth and death rates over time, or apparent birth and death rates if you can't distinguish birth and death from migration of the animal. So let's have a look at how Popan models work for this kind of data. So again, Popan models are a family of models for estimating population size and demographics for capture-recapture data in open populations. They're descended from Jolly-Seba models, and sometimes they're still called Jolly-Seba models, which were the original models for open populations. And Popan models were developed by Schwartz and Arneson in 1996. So The first difference between Popan models and closed population models is that they replace the parameter n, the population size, with n sub s, which is called the superpopulation size in the likelihood. So the superpopulation is the set of animals that are ever exposed to capture. So any animals that were alive in the population during one of the surveys. So for closed populations, the superpopulation size is just the population size because it's constant over the survey, over the study. But in open populations, the population size could change, but the superpopulation size is a feature of the whole study. So it's just one number. We don't actually care about the superpopulation size, but we're going to use it to estimate the population size over time after we fit the model. And so the reason we do that is that you can preserve the same likelihood structure, the multinomial or binomial distribution, by just replacing n with ns. And then this same likelihood structure applies to the open population study, because all of the animals that were ever observed during the study, or I should say which were ever exposed to capture during the study, still have to be divided up into a multinomial or a binomial distribution in the same way that the population was for a closed population. So now you just have the binomial distribution here dividing all the animals that were ever exposed to capture into those that were observed and those that were not observed. And you have your 1 minus the probability of observing an animal to the power of the number of animals that were never observed out of the superpopulation size. And then here we just have the capture probabilities for the animals that are observed, the same as before. So this is another really clever trick, right? Extending the multinomial distribution into open populations now. Okay, so Popan models need to model animals entering and leaving the population. And they use that using these two kinds of parameters, survival probabilities and entry proportions. So similar to CJS models, the parameter phi, and I'm using sub t, represents the apparent probability that an animal survives from time t to time t plus 1. So it's apparent because you might not be able to separate it from migration, from an animal just going to another area, leaving the population, but not dying. And whereas for every survey time in your study, you'll have a capture probability, you're only going to have one fewer survival probabilities because it operates between surveys, so from one survey to the next. And we also have these pent parameters, I'll say pent sub t, where pent sub 1 plus all of the other pents up to pent k add up to 1. So these are the proportions of animals entering the superpopulation on each occasion. So using the survival probabilities and the entry proportions, we can estimate the population over time from the superpopulation size using a recursion. So we're talking about the expected population size. over time. And so the expected value of the population size at the time of the first survey is just equal to the first entry proportion times the superpopulation size. So this is telling you how many animals you would expect to have entered the population or entered the superpopulation on the first survey period. And we're assuming that the whole population is exposed to capture when we do our surveys. So we expect that we see the whole population at time t equals 1 on the first survey. And then for any t, the expected population size is the expected number that survived from the time before. So that's the survival probability. Actually, this should be t minus 1 here. So the survival probability for applying to the time before multiplied by the expected population size at the time before. And then to that, we have to add the expected number that enter the population at time t. So this is the entry proportion times the superpopulation size. And so we have our base case, and then we have our recurrence relation going from the time before to the next time. Okay, now similar to CJS models, we need to find the probability of trailing zeros in a capture history using a recurrence relation. So given that the animal is alive in the population at time t, which we usually would be talking about the last time when the animal was captured. So we know that it was in the population then. The probability that you never observe the animal again is given by this recurrence relation. So the base case now is the last occasion in the study, so survey number K. So if you see the animal for the last time in the last survey, then you can definitely never see it again. So the probability of not seeing it again is 1. And then for any time, given that the animal's alive at time t in the population, the probability of not seeing it again is 1 minus the survival probability for that time t, which means that the animal has died at time after time t, before time t plus 1, plus the probability that the animal survives to the next time, but is not observed then, and is never seen after that time, given that it is actually alive in the population at that time. So that's the recurrence relation for trailing zeros in a capture history. And this is actually the same as the chi sub I from lecture 3 on CJS models. We're just expressing it a little differently. So the recurrence relation in lecture 3 was expressed in terms of the probability of being seen again, whereas we're expressing it in terms of not being seen again. So it's just 1 minus the probability of not being seen again. And this is the expression that was given in lecture 3. And if we just expand that out, and then we can factor the chi of I plus 1 out of this expression. And then if we just solve for chi here, we end up with the same expression as on the previous slide. So it's just exactly the same expression, the same idea. It's just expressed a little differently. And then the key difference from CJS models is that Popan models also include the non-captures before the first capture for each animal. So remember, CJS models only model the capture histories after the first capture of the animal, because before then you don't know whether it was alive or not, so you can't model survival. But Popan models do model those non-captures before the first capture for each animal. But you have to, again, separate the possibility that the animal has not yet entered the population versus the possibility that it's entered the population, but you just haven't observed it. And so, again, you use a recurrence relation. This time, the base case is the first survey. So if you capture the animal for the first time in the first survey, then the probability that it's never observed before then, together with, so it's the joint probability this time, that the animal is alive in the population in the first survey, is just the first entry proportion. So if you capture the animal in the first survey, it must have entered the superpopulation in the first survey. It couldn't have entered before then. Now, remember, entering the superpopulation just means being exposed to capture for the first time. So an animal could never be exposed to capture for the first time before the first survey. Right? And then the recurrence for any survey at time t, psi t is, so now the joint probability that the animal's never observed before time t and that it's alive in the population at time t is the probability that it was never observed before time t minus 1, but was alive in the population at time t minus 1, that it's not observed at time t minus 1, and that it survives from time t minus 1 to time t. So that would mean that you'd never observed it before time t, but it's alive at time t, plus the probability that it's just entered the population at time t. Okay, now that we have the probabilities for leading and trailing zeros, we can express the probabilities for the whole capture histories. So for an animal I that's first caught on occasion F and last caught on occasion L, the capture history probability is given by this expression. So here you have your psi F. So this is the joint probability that the animal was never observed before F, because it's first caught on occasion F, but that it is alive in the population at occasion F, because it is caught on occasion F. And then this expression is the product of all of the capture probabilities or non-capture probabilities between the first and the last captures of the animal. -1 here because we also have to express that the animal is surviving during that whole period. So the animal survives from time F when it's first captured all the way to time L when it's last captured. But remember that the last survival probability that we need is phi of L minus 1, which represents that it survives from time L minus 1 to time L. And then we just need the last capture probability, P sub L here. And then this is the probability of all the trailing zeros given that the animal was alive when it was last captured. And so the notation that we're using is C, which is the set of all the occasions when animal I was captured. And we're using this identity function I sub t is a member of C. So if t was an occasion when the animal was captured, then I is equal to 1, which means that you will have this factor in this expression here, and you will not have the factor for the non-capture. Actually, yeah, I might need to change this because we also need to express that you will have this. Oh, yeah, that you will have this factor here if it's not captured. So I might need to think about updating this slide, sorry. Okay, so yeah, I think I've explained this intuitively. So let's go through some examples. And I should say I'm using very simple examples just to explain how this works. You would very rarely have a 2-survey study for an open population just because you really are going to have trouble with parameter identifiability. So I'll talk about that more later, but just noting that this is not very common that you would have this for Popan models. And also, when this is not a Lincoln-Peterson study now, even though it's 2 surveys because it's an open population. But so say we have a capture history 1-0, so there are just 2 surveys, and the animal was caught on the first in the first survey, but not in the second. Well, psi1 is the probability of not observing the animal before time 1, given that it's in the population at time 1. So that's just the probability that it's entered the superpopulation at time 1. And then chi sub 1 is the probability of not seeing the animal after time 1, given that it is alive in the population at time 1. So that's 1 minus the survival probability. That's the probability that it might have died, plus the survival probability at time 1 times the non-capture probability at time 2, and times the probability of not observing it again after time 2. So representing that it survived but was not captured and was never seen again. And again, the probability of not observing it after time 2 is just 1 because there are no surveys after time 2. So then the total capture history probability is just psi sub 1 times the capture probability for occasion 1 and times the probability of not seeing it again after time 1. Yeah, and I've explained that. Okay, another example. So this capture history 0-1, so it was not captured on the first occasion, but it was on the second. And now psi sub 2 is the probability that it was not observed before occasion 2, given that it is alive, well, together with the fact that it is alive in the population at time 2. So it could have entered the population, the superpopulation at time 1 and not been captured, but survived till time 2, or it could have just entered the superpopulation at time 2. And then the probability of not observing the animal after time 2, given that it's alive at time 2, is 1 again, because there are no more surveys. And the capture history probability is just this expression. So now it's just psi sub 2 and the capture probability for survey 2, and then chi sub 2. Okay, and the last example is this capture history 1-1. So again, psi sub 1 is just the first entry proportion, and chi sub 2 These are different now because the first capture is not the same as the last capture. Chi sub 2 is 1 again. And now the capture history probability is psi sub 1, the capture probability for occasion 1, and then we have phi sub 1 because the animal must have survived to the second occasion. And then the second capture probability and chi sub 2. Okay, the last thing we need is the detection probability, which we're calling p sub theta still. So the probability that the animal is detected at least once during the study. And we find that value from the complement, so from the probability of never observing the animal during the study. And that probability is just the sum of the probabilities of the animal entering the superpopulation at that time, not being captured, and then never being seen again. So it could have entered at time 1 and not been captured, and then never been seen again. Or it could have entered at any time and not been captured and never been seen again. So if we just add up all of those probabilities, that's the probability of never seeing an animal. And so, we can just rearrange this to get the expression for the probability of seeing the animal at least once. Okay, and that's everything we need for the definition of the Popan likelihood. So we have the likelihood as this binomial detectability structure, but now in terms of the superpopulation, we have our definition of the, well, here it's in terms of not detecting an animal, which we can put directly in to the likelihood here. We have our capture history probabilities in terms of psi, chi, and the capture probabilities and the survival probability. And we have our recurrence relations for chi and psi. So it's a pretty complicated model, as you can see. And I think this is probably enough for this section of the lecture. And in the next section, I'll be talking more about parameter identifiability issues and an extension of Popan models to models which give us an estimate of the population growth rate over the course of the study, assuming that it's a constant growth rate for the population. And I'll also talk more about model fitting and probably about how to actually compute this kind of likelihood. So I'll see you then.